Then welcome everyone to today's Julia User Group Munich session. Still an online format. I'm very happy to have this because Julia itself is all over the world, and I'm glad we still have this format all over the world. Today, Dmitry Bagaev is with us, calling in from the Netherlands, actually from Eindhoven. He's working there since his PhD and doing a postdoc today in Eindhoven University. And yeah, in this lab, you already see it on the screen, the Bias lab. And same time, he's actually working in his own startup, Lazy Dynamics. He might tell you a bit more about it. But the company basically tries to really commercialize and scale this Bayesian inference. So all the luck to him and his crowd. And now stage to you, Dmitry, for this introduction to fast and scalable Bayesian inference. Thank you so much for being our guest.
Thank you very much for inviting me. Yeah, I really like to present what we do. So, and thanks for the introduction. So it was very nice. So yeah, my presentation will be about a package in Julia, which is called RxInfer. It's available online and it's free. And the subtitle of the presentation is like a path to fast and scalable Bayesian inference. And it may sound a bit complex for like people unfamiliar. What is Bayesian inference? Like what is fast or scalable about it? But we are going to dive into that some details, of course. So let's see how do I make next. Okay, so and I usually like to introduce like a probabilistic programming. So essentially Bayesian inference and RxInfer.jl package in particular is a package for probabilistic programming. And usually the next question is like, okay, what is this probabilistic programming? We have programming, right? Why not just programming? And let's try to imagine a situation, right? We want to build a drone, and we just use a regular programming, and we have some data for it, right? We have some algorithm that runs on this data, and this drone, I don't know, it needs to fly somewhere. Right, and we feed some data to it, and then we get some result out of it, and it all works fine. Until we actually hit the reality and we realize that all our data is actually some sort of uncertain, right? We don't really have a precise measurement of the velocity, and we don't really have a precise measurement of position, and we can have some external factors like wind speed. We cannot really pre-program it. So, okay, so what we actually can do, we can assign a distribution to a certain variable in our algorithm. And then the question is like, okay, but how do we compute the result? So we don't really have any precise value for like velocity, position, but we need some sort of result, right? We need to fly somewhere. So this is actually essentially the example for why do we need the probabilistic programming. Probabilistic programming tries to deal with this kind of situations where we don't have a precise value for some values in our data sets. And the applications are everywhere, right? Like starting from pharmacology, actually, this COVID example is a very good example, right? We had so much uncertainty about how it's going to progress. In climate modeling, we have a lot of uncertainty, logistics, robotics, and so on, right? So essentially, every application has it. Every signal processing application has to deal with some uncertainty in their data sets. And the backbone for this, it's actually good news, is that it's kind of solved. We have the Bayes rule that basically defines the most logical way to update our posterior information based on new evidence. So we have some sort of a prior about our parameters, and we observe some new event, and we update our posterior. It's pretty simple. The formula is really simple. This is the whole formula, right? But why is it so challenging then? Why the packages are around there, or like the whole community doing that? Because essentially this formula is just like one multiplication and one division, right? If you just look at it, just nothing really spectacular. But then, yeah, the devil is in the details, right? So okay, we start to apply Bayesian inference and the Bayes rule in this setting for the drone, right? And we have a small system that includes 3 parameters, and the math turns out to be quite simple actually. So we can solve it, and there is no problem at all. But then, if we start add more components to our system, it becomes a bit trickier. So the math becomes a bit more complex. The complexity grows exponentially. But we want more. We want to add like not just velocity, position. We want to add some like video, audio. We want to add physical constraints of the world. Maybe the power engine is constrained. There's some environment constraints. So it blows up pretty quickly. It's like if before we could actually write down the math and solve it, at this point we cannot even write it down. It's just like super complex. But we actually want even more. We want to add as many components as we want, and we don't really want to think about all of this math behind. And not all people in this world, they have a PhD, right, to understand all of this. It's pretty tempting just to have some sort of like a package that does it for you. And here I want to draw an analogy with like just a regular programming, right? So before, back then, people actually needed to be like scientists to write code. They were scientists, and they started like, and it was a very tedious process in the very beginning. But nowadays, yeah, we teach it in the universities, right? The students just download Python, and yeah, they just write programs, and they don't think about all of the complexities of the modern computers. It's all hidden. The compilers do it for us automatically, or interpreters. But with probabilistic programming, it's kind of still not there. With probabilistic programming, it still requires a lot of understanding how does it work. So the packages that are currently available, they do help, but still it's still not there. It's not as easy as using like Python, let's say. And this is where probabilistic programming essentially needs to go and evolves to this kind of a very robust systems that that help you to create robust systems that makes reasonable actions under uncertainty in unpredictable environments. And what we want essentially is we want to have as many components as we want, compile, test, and deploy this kind of systems with probabilistic programming. Before I go to the next kind of section, are there any questions so far? Okay. So how does RxInfer approach it? Because essentially there are many packages for Bayesian inference already in C++, in Julia, in C#, in Python. So yeah, the choice is big, right? So why did we decide to make yet another probabilistic programming library? So in Bayes lab in the university, we work with autonomous systems, and this has a pretty unique set of requirements for this kind of a probabilistic programming systems. So it must be scalable because these autonomous systems, they need to operate in a real world environment, and real world is complex, right? It has many variables and they interact with each other, so it must scale. It must also be low power because these drones, they really have a pretty limited power budget. It must be adaptive because yeah, real world is chaotic, so we need to be able to adapt to it. It must work in real time because we need to react quickly. It must be performant, and it must be also robust, right? We don't really want to have a second delay and our drone hits a wall or like someone's car. We don't really want to do that. So this set of requirements is why we decided to make a new package, because in our opinion, none of the packages that existed before, they actually focused on this specific set of requirements. So indeed, some packages, they're very performant, right? Or maybe they scale really good, but they maybe consume an enormous amount of energy, or maybe they require GPUs. So that then means they are not low power. So in order to approach that goal, essentially, we have three key components in our recipe. So we work with factor graphs, we do variational inference, and we do reactive message passing. So essentially, just a little bit of introduction, right? A factor graph is a factorized representation of a program, let's say, right, of a probabilistic program. And probabilistic program essentially is a generative model, is that your belief about how data is being generated. And this model, it can have some hidden states, right? The states that we cannot directly observe. For example, theta or gamma or S1, S2. So this kind of states we cannot observe. But we can observe something else. We can observe Y. So imagine if we are talking about the drone, so we can partially observe the position of the drone, but let's say we cannot really observe the wind speed, current wind speed, because we don't have a sensor for it, right? So the wind speed is a hidden state in this setting, and the position is our observation. So we can create a model for this. We can inject some sort of like a background knowledge in this model. We can inject the physical equations, how a wind speed would affect the position. And then by observing the position, we could infer the wind speed. And RxInfer essentially comes with a model macro that takes the textual description of a probabilistic model and converts it to a factor graph. So for people who are familiar with Turing, for example, Turing is another probabilistic programming library written also in Julia. It works a bit differently, but they also have a macro that is called model macro. And it also allows you to define a probabilistic model, but as far as I know, it doesn't really create factor graph under the hood. So in our case, like every statement does really create a factor, like a factor node in the factor graph. So if we have some variables in the model, they must be connected somehow. And on the screen, you see an example that actually directly translates to the factor graph, also on the screen. And the tilde is a special type of operation that means, okay, this variable, this hidden state, is distributed according to some distribution, right? Or is drawn from distribution. So, but we don't really know the exact value for those hidden states. They always have some sort of distribution. And the nice thing about factor graphs is that they actually can be treated as like sub-models. So in principle, we can define a small part of our model and then repeat it several times. Or we can create hierarchies, or we can create a model for, let's say, like audio processing. We can create a model for like wind speed processing. We can create a model for video processing, and we can combine all of them together in one super mega huge model. And this is what makes this approach very nice and scalable as well, because it kind of also directly translates to the notion of a function in just a regular programming, because we always want to decompose our big models into a set of smaller models. We want to analyze the performance of a small model first, test the small model, and then compose a big model. And because we actually have a direct structure of the graph, we can do some post-processing on that. So we can find like some local regions in this model that where we can apply some local optimizations, let's say, and make the model more compute friendly, let's say. So the second component in our recipe.
I would have a question, actually,
Yes,
Dmitry.
sure.
Can you go one part back to the sub model?
Mhm.
Like, yeah, because this definitely, or yeah, for some maybe a new thing. For me, actually, it is. So this submodel function does not really have a return value. So it looks
Yes.
like it's defining two things, and maybe that the last part is the returned, and probably it is. I'm not 100% sure. But yeah, in the model below, it's like, yeah, it's just this big S. So is this just for illustration purposes, or is this actually kind of working? And kind of, can you explain a bit about this return value and how it's used?
It's a very good question, actually, because I never thought about it, but there is no return statement. You can return something what you want, but essentially submodel is defined with its input arguments. So this you can see a submodel as a subgraph that has open edges, and these open edges are y, s next, s pref, theta, and tau. So essentially, in order to call it, we need to have n-1 variables defined on the right-hand side of the submodel, and the last will be inferred automatically. So in this case, I have y defined, previous state is defined, theta and tau is defined. So essentially what it says is that next state is distributed according to this submodel.
Thank you so much. Yeah, I was skipping this. Yeah, cool.
This is a very good question. I think we can also clarify it in the documentation, and it's an actual working example. So it's not for demonstration purposes. It's an actual way how it works. And this was a huge work done by one of our PhD student. He's actually he's also looking here. So Walter Nauta. So he did this great job of creating this new model macro completely from scratch, re-implemented, tested, very good, and with this new support for submodels. So yeah.
Yeah, thank you. This explains it.
Yeah.
There's actually a second question coming up.
Mm-hmm.
Are these local optimizations, so the slide thereafter, applying conjugate priors, or there's more to it?
Currently, it's also a good question. Thanks. Currently, RxInfer doesn't really exploit this feature of local optimizations, but this is something that we kind of really wish to work on. So, for example, what in principle can be done is that we can compress this kind of submodels or this region into one node, right? Why it can be useful. So if we do that, it means that we cannot infer the value of the variables that are hidden in this box. So we compress it. But why it can be useful is that then we need to do less computations, essentially. I can talk a little bit about that in detail about when I will talk about message passing. But currently, RxInfer doesn't really do anything super special about this local optimization. It's just a nice property of a factor graph that we will exploit for sure. I think we actually have a yes. We have it in mind as like a small sub project actually to compress these models, because we know for specific configurations of the node, we actually know analytical solutions. This also includes conjugate relationships, but not necessarily, not always. So we could compress this in the graph if, for example, user is not interested in the variables that are in between. And then we can use analytical solutions that are way faster than doing just some approximations. I hope that answers the question.
In addition, also Albert answered a little part of the question. Thank you very much, Albert.
So yeah, I also see the chat. So if you have questions, just ask, and yeah, we'll try to answer. So that was an introduction to the factor graph, but the second okay, so we have another question, sorry, before I start. So there are specialized PPL for state space model like Birch. Is this package particularly for sequential latent Gaussian state space data? It's a very great question. No, it is not. It is not specific to state. Just one example. But actually on our website, on GitHub, we have a lot of examples. Just I will also refer it in my presentation later a bit. But no, this is not packaged specifically for state space models. It works well for state space models, and we had state space models in mind because, as I said, we work with autonomous systems, and autonomous systems, they usually progress using some sort of a state space model. That's a very natural choice for models. But the package itself is not specific to space model, and you can also use it for ID data or some other data, linear regression as well. We have an example for linear regression. It's all possible. This is a very good question. Okay, so the second component is variational inference. So basically, instead of solving the Bayes rule directly that I was talking in the beginning, we do a so-called variational inference that reframes the original problem as the optimization problem, subject to some constraints. So I have a formula, and we need to minimize the value of this given some Q from the family of Q capital. And what this essentially does, it tries to approximate the real solution with some sort of a parameterized distribution, for example, from a distribution from exponential family. So let's say a Gaussian or a gamma or a Poisson or Bernoulli beta. So all is possible. But this makes the task significantly easier to compute. So the good thing about this approach is that we actually may decide not to impose any constraint, in which case it is equivalent to the Bayesian inference, just the exact Bayesian inference, which is also possible in some scenarios. But usually it is beneficial to impose some sort of constraints to reduce this computational load and to get the result faster. Of course, the result will be an approximation, but in most of the cases, the approximation is really good enough in these scenarios. So there is no need to run a very extensive exact Bayesian inference procedure where we can just impose a set of simple constraints and get the result much faster and with reasonable accuracy. And for that, RxInfer imposes a macro, which we call constraints macro, that allows you to put some constraints on specific posteriors over some variables. For example, we have a hidden state S or a sequence of hidden states S, and we can say that we actually know that they are independent, right? So, and then we can also say that posteriors over S are all Gaussians. So we want to approximate them with a Gaussian. So the first constraint is usually referred to as mean field constraint. It's a very popular choice. And the second type of constraint is that we call a functional form constraint, where we impose a specific functional form for some specific hidden state. And the last component in the recipe is message passing technique, and which we also call, and we implemented a specific version of this, which we call reactive message passing. That was the main topic of my PhD dissertation. So essentially, this is a very tricky and very mathematically involved. So I will just ask you to believe me, but the variational inference here can be implemented as passing messages between nodes in the graph. This is very mathematically involved, but it's possible. So essentially what is happening is there is each node has to compute a specific function and send this as an information. And in order to compute the posterior or solve the Bayes rule, essentially, we need to take two messages that are colliding on the same edge, and we need to compute a specific value out of it. So there are formulas for that. They're very like huge and big. This is what I was talking about in the beginning, right? It's like, even to understand those formulas, you need to spend several years. But we want the users not to think about it much. Want it just to work, and we do all the mathematical burden behind the scenes. So, but just the concept of message passing is relatively easy to understand. We just send some sort of pieces of information around the graph. They somehow collide with each other, and at the end, it forms the result, essentially. What is cool about this particular reactive implementation is that it actually robust to failures, because if, for example, a specific sensor fails or like a specific part of the graph fails, we just stop reacting on the messages, but the rest part of the graph still may proceed with computations, because usually with conventional message passing implementation, there is a sort of like a gut schedule that decides in which order to send messages. And if some message cannot be computed, the whole schedule needs to be recomputed entirely. And this doesn't really scale because if a failure happens, you need to stop the entire system and reschedule the messages, which means you will have a 1 second delay and you will crash into a car, right? So in case of a failure, we still need to operate. And this is why reactive message passing helps with that. So it just keeps reacting. So every time we have a new observation, we have a new message, and it just flows through the graph, and all other nodes are just reacting. And if there is no other information, they just wait in idle mode, or they may improve their approximation locally. But essentially, there is no pre-computed schedule, and it reacts on data as soon as it arrives. And it also makes it possible to hook up like data sensors that have a variable update rate. So for example, if we have audio and video in our model, video is like usually 30, 60 frames per second. So there's like 60 data points per second, let's say. And for audio, it can be 44 kilohertz, which is much higher update rate. So basically, with conventional message passing approach, we would need somehow synchronize all this, somehow come up with a schedule that deals with that asynchronicity. But with reactive message passing, it's basically by design, because we don't have any schedule. It just reacts on new information. If there is new information, yes, we need to proceed with this new information. And if we don't have any new information, we just do not update our posterior locally. And just to, again, summarize all of this, right? So probabilistic programming, we need to specify our generative model. And in RxInfer in particular, we need to solve variational inference. So we need to solve an optimization problem. For model, we have the model macro that just translates the mathematical description of your process, the real-world process, into some sort of a graph. We have the constraints macro that helps us to impose the constraints into optimization problem, and RxInfer deals with the mathematical burden of all of this under the hood, right? It just solves it. And the cool thing about our API is that it also supports dynamic data streams. So because of the reactive nature of the message passing, we can actually work with infinite data streams, right? So we can hook up a sensor and we can just run the model, and it will update its posteriors as soon as data arrives. It's very different from other solutions that usually prefer a complete data set to start the inference. In our case, it's not the case, essentially. So you can start inference even with the partial data. You can also see the examples of it in the documentation, but I also will show you a small example later on. So essentially, we believe that this cocktail, let's say, of factor graph, variational inference, and reactive message passing is the way to proceed with this unique set of requirements that we imposed in the very beginning. And it all transformed into a package, RxInfer, and we have a website. You can check it out. It's also available on GitHub. It is available in the Julia package registry. You can just add it very easily, right? And we maintain it. It has a lot of updates every month. And for example, you're also familiar with Turing, most probably. Just to draw a line between us and Turing. So Turing is a really good library. I actually also use it. Also to compare our results, how do they perform, how do we perform. But essentially, we just have a different set of requirements. So for RxInfer, it's really about fast inference, about scalability, efficiency, and supporting reactive data streams. And for Turing, it's more about universality. It's like plug-and-play solution. It's easy to use. It has different algorithms. HMC, it also supports variational inference, NUTS, HMC, PG. So they really want to be universal, and we really want to be efficient, right? But of course, Turing team works hard to make it more efficient. And we are, on the other hand, we work hard to make RxInfer more universal. So, and at some point we will collide, I guess, and create the best ever probabilistic programming language in the world. This is also a small slide about why we want to RxInfer be as efficient as possible, because we have some small projects where we run it on Raspberry Pi. And as you can imagine, Raspberry Pi doesn't have a GPU to do like extensive sampling. It actually has a pretty bad CPU, and it has a pretty low amount of memory. And running like, let's say, sampling-based procedure, which are very popular in the Bayesian inference community, it's not really feasible on Raspberry Pi, at least not in real time. So like if application does not require to be in real time, that's maybe okay. Still, it's very challenging. Do we have questions so far?
Yes, I would have one question for because you already showed the Raspberry Pi. It's probably rather a question for later, but I'm really interested about the memory part. So I know that kind of the CPU kind of is really cool, optimal, but the Julia itself, of course, has some overhead probably, just loading Julia, I mean,
Yes.
in the memory field. And
Yes.
have you kind of encountered this as a limitation, because it seems like you're working with even lower systems, like in Raspberry Pi is already kind of very high level.
It's a good question. The answer is yes, we did encounter problems with Julia, because just to start Julia, it requires like 0.5 GB of memory. So, and in order to use Julia code efficiently, it is better to pre-compile it ahead of time to reduce this kind of, also like a compilation requires memory, and then it stores this result. So it is still pretty hard, but it's possible. So we did actually this. It was difficult, but it's still significantly easier than using a sampling-based solution, let's say. And as far as I know, Julia also improves. So in general, right, I really hope in the future it would be possible to precompile entire application. Now it's really like not the case. Garbage collection is still really an issue which makes us really think hard in terms of how do we write our code such that it allocates less, such that the garbage collection triggers as less as possible. So it's a challenge indeed to do that.
Very interesting. And I think it's also chicken egg problem. Yeah, if there are more cases for Julia which use these or which have these requirements, yeah, then there's more pressure for the language itself to evolve in this direction.
Yes.
Yeah, but yeah, I'm super curious and would be interested to also get more details on this. There was one hands up. I'm not sure whether there's still a question. I wasn't quick enough to see who was it.
Yeah, I have a small question to Dmitry about this boundary Turing and RxInfer, and basically how he, from a user's perspective, will divide RxInfer and Turing. For example, if I want to obtain a reasonably good posteriors with a reasonably sized data set in unreasonable amount of time, I will just take MC, put my dataset into Turing, NumPyra, wait for day, week, obtain my posteriors, report it in my paper, and I'm done. But what is kind of ideal use case for RxInfer?
It's a good question, very good question. So if you have a reasonable amount of time, yes, you can use Python. Probably yes. But I don't know anyone who has a unreasonable amount of time. So I think generally RxInfer is built around this set of requirements that I was mentioning earlier, and most generally it's about autonomous systems, right? Where we really need we have some probabilistic models and it's coupled with some sort of actions that needed to be performed quickly. It's not necessarily like millisecond reaction time. It can be a second, or in some situations more or less. For audio, it's less. For, I don't know, for traffic lights, it's a bit more. But essentially, RxInfer is best if you have a large model and you need inference result relatively quickly and with like and this always will be an approximation of the result, and where you don't have a lot of memory and you need to react fast. So that's kind of a borderline, I would say. But there are also many applications where it's not necessary, and this is also the reason why Turing is so popular, because it's not always the case where we need to run inference in a second scale. Sometimes it's perfectly reasonable to run it overnight or even over a week. It's actually what happened with COVID, as far as I know, because the data, it's also about how fast do you get data. So again, for audio, we get it relatively quickly, right? 44 kilogram per second. But with COVID, it was like once a day, right? We have a new observation, like number of infected people. And yeah, if your data updates once a day, it's reasonably okay to use Turing, because yeah, we can wait for a day. Albert also hinted in the chat, yes, that's it might be good to prototype. So it's actually what we do in our lab. As well, because inference is fast, relatively fast to Turing, we can iterate on the model quickly. So we don't need to wait for an hour just to understand that our assumptions in the model were actually completely wrong and we need to rethink. Right? Instead, with RxInfer, we can iterate quickly. We can wait for several seconds. Okay, the results are actually completely wrong. And then you realize that you made a typo in your model, and then you iterate, this loop becomes way faster, and then you can converge to a good model or a good probabilistic program faster. There is another question in the chat. Can we specify structures in DVI constraints like sparse precision matrix or factor structures? Yes. So it is not the same as ADVI, for example, or like black box variation inference, where they essentially impose a very huge Gaussian, and then they impose some sort of like structure in it. I think they call it a guide or something like this. It works a bit differently. So in RxInfer, we really have the structure of the model, right, in terms of the graph. And this graph also defines which variables are conditionally independent, which additionally imposes already a factorization constraint on this kind of a matrix. It's not really a matrix, but anyway. So yes, we do have like a default factorization constraint for the model, but user can additionally specify more constraints. So for example, here we specify additionally mean field constraint, but we can say that, for example, state 1 and state 2 are actually conditionally dependent and all other are independent. Or we can say that, let's say in this example, that tau is conditionally independent from gamma, right? Or tau is conditionally independent from S1 and S2. So this kind of constraints are possible. Yes. I hope that answers the question. There is a question in the chat. Could I tell more about the beta free energy? Yes. So beta free energy is essentially the metric that we are minimizing when we are solving the variational inference optimization procedure, and it basically an approximation to minus log evidence in the Bayesian inference setting, and it shows how well your model performs essentially under the data that you observe. And in principle, you can even use free energy to decide what kind of model is better for this particular data set. It also is being used as a performance metric to understand if your result actually converges. So in some situations, because it's an optimization procedure, it needs to do some sort of iterations to converge. And beta free energy is a metric to find, to check if the result actually converges. The tricky thing about beta free energy is that it's not always also possible to compute it, even in RxInfer. So the optimization procedure can be done without computing beta free energy explicitly, because as I said, the whole optimization procedure is reframed as message passing. So there is no explicit differentiation happening. There is no like in ADVI, for example, right? Automated differentiation, variation inference. We actually we don't use like any automated differentiation. But of course, free energy is possible to compute, and RxInfer provides an API for it. It's just not always possible. But if it's possible, it's very good to check the values of beta free energy. Does the model actually make sense for this particular set of observations? So, do I have more questions, or I just will proceed? I think we are a little bit on the second half of my presentation, but we still have time, I guess. So, okay, so the next question is like, does it really work? So we had this unique set of requirements like real time, super efficient, no memory allocations, run on Raspberry Pi, super fast. So is it even possible? So I have a small kind of an example, right? So let's assume we started our presentation with a drone. So let's do a drone, right? So we know the dynamics of the drone, given we know the parameters of the drone. Let's say given we know the mass, given the size, where the propellers are, we actually can define an equation, a physical equation, how it should perform. But of course, how it should perform and how it would perform is different, right? Because in real world, the sensor may fail, the wind may interact, but we define the dynamics of the drone in some function, and then we can also define a probabilistic model of the drone, how it would behave. And so the way the model on the right-hand side of the screen is written is such that we have some prior over initial state of the drone, and we unroll it into the future using the state transition to estimate where it's going to be, where it's going to end up. And we set some sort of a precision around the state transition. And at the end, so the way the model is framed, we want to reach it some goal. So in my model, I have the states S, which are basically the position, the angles of the engines, and the power of the engine, basically, and the acceleration of the drone. And then the state somehow progresses, and we also have an action in. So U is the action. Basically, what we want in this probabilistic model, we want a drone to reach the goal. The goal is set at the end. So we want the last state to be a particular value. And we have some actions that we don't know. We don't know the value of the action. So the task here is to infer, given the initial position and the last position that we want to infer a course of actions. And we don't know. We don't know what kind of an action to do. So we put a wake prior in it, and we run inference. And basically, if we just run this kind of model, this is what is happening, right? So the red cross is the goal, and it changes constantly, right? Just for the sake of the example. And the drone constantly infers the best possible action that it needs to perform in order to reach the goal. But the thing is that it also doesn't really know its real position, because the sensor has some noise, for the sake of the example. And also, for the sake of the example, we have the sliders below that change the world. So that's why RxInfer, I mentioned, has this reactive message passing, is that inference is happening constantly, and the world changes constantly. So the inference must adapt to those kind of changes, no matter what. The drone's mass cannot really change. That I understand that, but for the sake of the example, right, we can change the mass of the drone, and then it needs to react on that. It needs to update its posterior about its own actions. For example, engine power can change, maybe because we don't have enough battery anymore and want to save battery. So engine power changed. So the inference must adapt. It must update its posterior. Sensor noise, I don't know, broke, and then we have more noise. It needs to adapt. There is a comment in the chat. If it's a delivery drone, the mass can actually change. That's a good remark. But let's say gravity cannot change unless your drone flies to the moon. But then yes, then it may change. So there is a question in the chat. Is there like a discount factor so that the robot forgets the long past? Is this hyperparameter? This is a good question. This is up to a user. So we have an extra set of macros, which we call auto update. Essentially, how do we want to progress our current posterior to our priors? This is written in our documentation in more details, but this is up to a user. So, and in my experience, it's better to include this forgetting factor. Yes, because essentially, indeed, if you run this inference for a very long period of time, your posterior may clamp, and then it becomes just computationally unstable in a sense. So, but again, we don't do anything special about that. User just they may need to decide on their own. So there is a question in the chat. So RxInfer also has a decision module, like policy optimization. No, but this is the result of the specific model that I showed before, right? So I designed my model in such a way that it includes a decision. In this case, it's called U. And I use this variable, it's a hidden state, to perform an action. So so this is also why Bayesian inference is so powerful, because on the first glance, it's just a base rule. It's basically that defines how to update your prior based on new observations. But you can compose your probabilistic model in such a way that you include a policy as a hidden state. And basically, you can infer the policy. Or better to say, you can infer a distribution over your policy. And then, given the distribution, you can take a mean like of the policy, or you can sample from this distribution to get to perform an action. This is exactly what is happening in this particular example. In this model, we encoded policy as a hidden state, which makes it a policy optimization essentially. But this is not the goal of RxInfer. It's more like a byproduct. I will also show you that we have so many examples with actions or with no actions, with linear regression, with IID estimation. But this particular example are kind of close to us because we work with autonomous systems, I would say. While there is another question is typing, I just want to briefly mention the kind of the power of this probabilistic programming approach is this. On the left-hand side, I have just this drone dynamics function. On the right-hand side, I have a model definition, and I call my infer function from RxInfer. And this is just like, I don't know, 40 lines of code or something. And this code in the center is the code that I needed to write for visualizing the drone. So actually, it was much easier for me, at least, to create this drone, to come up with this kind of a behavior than to visualize it. And this is where we want to go. We want user to work less. We want user to write less code and basically work on the application and not with the code. There is a question. The drone model function looks like an offline computation after the horizon is sampled. Can this be formed differently for online conjugate? So it looks like an offline, but it's actually, so it's just a huge model, but it's one online step. So this is why also RxInfer is aimed to be scalable. So this is a huge model, and horizon is not sampled, it's just set to a specific value, let's say 100. I don't remember a specific value for this particular example. But what is happening, this huge model is just one online step. So we infer the policy and we go forward. So yeah, it's actually, this particular model is used in online setting. So it reinfers every time. Every time we have a new observation for our current state, we reinfer the entire policy, which is huge, actually, indeed.
Maybe a similar question. So in this model on the right, we set the end index of our state, but the horizon might not include this if I'm right, or it might be that we just modeled steps before the end, or yeah, how does this connect the horizon to the end in the modeling?
So this is a tricky part of our language. So you see, I do not really define those variable s nor its length. So yes, it's a very good question. So, but basically the model macro keeps track of this state. So we defined S1, then we defined S2, S3, S4, given the horizon. Then we defined, the last one was S horizon plus 1. So it keeps track of the states, and it knows at this particular line, it knows that the length of S, it should be horizon plus 1, and it will be defined because we defined it here.
Thanks. Yeah, that makes sense.
So the question from the chat, so the horizon is just a hyperparameter for an upper bound of steps needed to capture. Essentially, yes. In this particular example, yes, it is a hyperparameter. But I didn't want to make this example extremely complex, so it's like it's already oversimplified. But of course, the model can be much more complex to actually capture the real dynamics. And this horizon, in principle, also needs to be a hidden state, right? So because we may choose a specific horizon for a particular problem, but let's say 100, but it might be too much, right? It's really true. So the horizon itself must also adapt under circumstances, under a new observation. Okay, I think I should proceed because we have a half an hour left. So let's, unless someone else also has a question. So as I mentioned, we have a bunch of examples on the RxInfer documentation. This is a bit of an old screenshot. I really should update it. But it actually shows the list. So now it's like in subcategories because the list was so big. So we decided to put demos into their corresponding categories. But it starts from state space models, as people also asked in the chat. But also we have a cool example about. It's actually a separate paper about path planning. So we can use RxInfer to plan a path given several agents wanting not to collide with each other, but like reach a goal. We have a real-time examples with the drone and all over. Like we have this notorious assessing people's skills, a very famous example, Gaussian linear dynamical systems, autoregressive models. We have hierarchical models. Autoregressive moving average, infinite data stream, system identification problems. We have mixture, Gaussian mixture models, universal mixtures. We even have an example where we auto-differentiate the entire RxInfer procedure. So if you have a hyperparameter like say horizon, you can actually just auto-differentiate through it and use free energy as the metric to decide on the best horizon for a particular data set that you observe. But that, of course, will not be real time probably. Well, it depends on the complexity of the model. We have an example with invertible neural networks. We have examples for non-conjugate inference and like using nonlinear functions, etc. So I just encourage you to check out our documentation and maybe you find something else, or maybe you contribute a new example. That's also will be very cool. And we have some future short-term plans, let's say. So currently we started a project to visualize the structure of the graph, because I was talking about how cool it is to have a graph, we can analyze it. But currently the visualization is quite rudimentary, it's very simple. But what we want to have a really good visualization of the graph, ideally that we can just put it in the paper, right? We just created the model and we generated like some TXT file and then we put it in our paper. And currently, people from Active Inference Institute are working on that. So these are external collaborators. But if other people are willing to work or help with that, it will be very beneficial, right? And currently, we are also working on non-conjugate posterior computation. So usually when people start to use RxInfer, they quickly realize that the performance and efficiency comes with a price. And also someone mentioned it in the chat. So usually RxInfer prefers to work with conjugate models. So it means that the model must be composed in a special way to achieve this superior performance, because if this is the case, RxInfer can execute a specific rule to compute messages analytically, and it will be extremely fast. If a model is not composed in this specific way, or if a person is not experienced enough to find those kind of relationships, then RxInfer will throw an error saying this is it doesn't know how to compute a posterior in the most efficient way, for which we have this constraints language that in certain scenarios it helps, So we can guide our inference, or we can impose a specific constraints to actually compute the result, approximation of the result. But it's very limited at the moment. But we have a very nice extension coming very soon that will broadly like open or extend the set of models that we can run inference for. And this is based on new research that basically tries to approximate a specific posterior with a certain member of exponential family by projecting its natural parameters like to the closest, basically to the best solution. So it's also very mathematically involved, very difficult. But at the end, for a user API, it will be a simple parameter like, okay, we want this particular state to be projected on the closest beta distribution, for example. And just to quickly demonstrate how it works in particular, right? So this is a model. This is not a state space model, by the way, right? But this is a non-conjugate model. So it means that for this particular model, RxInfer by default will throw an error because we have some observations why they, let's say, come from a Gaussian, and let's say we, for whatever reason, we decided that the mean of this distribution for this particular data set comes from a beta distribution. It means that it's constrained from 0 to 1. But also the precision, the R variable is also constrained from 0 to 1. Then it comes from exponent, and then it becomes the precision of our observations. So it's without a lot of details, running inference in this kind of model, even though it looks very simple, is very challenging, extremely challenging. And let's say with our new constraints language, we can use the projection. So we say that, okay, T must be projected to a beta, R must be also projected to a beta, and K must be projected to a gamma. And the reason why it can be a different distribution, but for this particular example, the reason for gamma is that this is a conjugate prior for the precision parameter of the normal. So I decided to put gamma. And then I also say that, okay, variables TR and K are conditionally independent. So I impose a factorization constraint, as also was asked in the chat. And then there is a new macro that I didn't really mention, but basically it defines an approximation method for exponent, for the exponent function. And in this particular example, it's also a projection, but it's called CVI for basically historical reasons. There's a paper, conjugate variational inference, that started this project long ago, and now it is being improved with the new technique based on the projection. And yeah, we can just call the infer function from RxInference. In this particular example, it's not using online data set, it's just a fixed data set. So it's not really necessary, by the way, I didn't mention that, but it's not necessary to use RxInfer for reactive setting. It can work with static data sets as Turing as well. And then we put constraints, we pass our meta, we have some initialization for parameters to start the inference procedure. And we have this new option. We will have this new option for the rule fallback. So currently, if the rule for message is not available, RxInfer will throw an error. But with this new option, it won't. It will try to compute a generic message. And then we have a pretty good, so I generated some data, right, for this data set, for this model. I chose some parameter for T, for R, and for K. And we can see that, for example, if I have 1,000 observations, we can run inference in milliseconds, and it infers it pretty much like really good. Like the inference results, in my opinion, are really, really good. Given we cannot really recover values precisely, never, because this is the whole idea about Bayesian inference, to have a distribution, the best possible distribution that describes the data that we can observe. And we can see that it found pretty reasonable posteriors. And if I run the same example with Turing, with sampling, I can see that nuts is a bit slower and gives some sort of a result. They actually do not give the posterior over k, because k is linked as a deterministic function to r, so they don't really return posterior of that. But I can also observe, so and on the right side, it's ADVI, also from Turing, and it's actually faster, so which is good. But we can also see that the posteriors are kind of more opened, so the variance is bigger. Another distinction is that Turing does return samples, but we actually return an actual distribution. So in our case, because we projected on the beta or on the gamma, we can work with parameterized distribution, and we do not really need to carry a list of samples for that. And just a small disclaimer, right, about this particular example is that the real performance depends on many things, right? Hyperparameters like your computer memory, if you use GPU. So I'm pretty much sure that Turing can be made faster in this particular example, but I'm also pretty much sure that RxInfer can be made faster in this particular example. It only shows like the default setting, so I didn't change any hyperparameters, just called nuts, just called EDVI, it's very default. And also for RxInfer, I just called the default. But with all algorithms that involve some sort of hyperparameters, it is possible to make it faster or slower. So just a small disclaimer, right? I'm not trying to say that Turing is slow in this particular example. It's actually not, because ADVI does it pretty much good. So, is there a yeah?
Yeah, one question to this. The ADVI is probably automatic differentiation, variation inference,
Yeah.
something along this line. And this question I actually, it's in my head for a longer time already. So if you're not using automated differentiation, isn't there kind of, or my intuition would say you miss some important information which you just could use, but this seems not the case. The message passing is actually really efficient. But can you kind of give an intuition why it's not so important to take the advantage of knowing the differentiation?
Okay, I didn't really understand the question, maybe, but I can interpret it in my way. So
like you're also doing variation inference, and
yes.
and the ADVI kind of uses all this framework around taking the differentiation automatically, like huge prior work, and you apparently don't need this, and this is a bit of a cognitive surprise for me.
Okay, I think I understand better. So the real power of ATVI is that it treats the model as the black box, right? So the entire model, it's just one function of all variables, and it can differentiate through it, and it really doesn't care about the structure of the model, and it gives reasonably good results. For us, we actually need to care about the structure of the model. So and this is the current problem that we are trying to solve with this new approach. The real problem is that we cannot compute messages in all situations, because we care about the structure, and because we do this local computations. We need to do this local computation. So ADVI doesn't need to do this. It does the global optimization as a black box, but we do local optimization. And in some situations, these local optimizations are actually difficult to execute. So this is what this new method based on the projection aims to solve. So it provides a very generic framework to approximate these local computations. In the same way as a NUTS is a very generic way to compute posterior, and ADVI is a very generic way to compute the whole posterior over the whole model, the projection is a very generic way to approximate local computations. That makes this approach very nice, in particular for RxInfer, because we need to do that, and it it kind of this expands the set of models that we can run inference for.
Yeah, thank you a lot. There's also other questions in the chat coming up, but one
Yes.
follow-up. So could you still use the differentiation kind of for this local message passing? Is this just really kind of completely different way of doing things, or could you also use differentiation to kind of compute the better direction in some way?
We actually have approximation methods based on a forward if. Yes, it is possible, but they are limited. They are more limited. But in general, for example, we have linearization, what we call linearization, that tries to compute the first derivative of and tries to approximate the nonlinear function as linear function, and then uses analytical updates for linearized version of the function. So this is also possible, but this is also very limited. So this new approach is better.
Thank you.
And there is another question in the chat. So ADVI is much closer to the truth than RxInfer, where truth is being defined as HMC. Well, HMC this is actually nuts, but okay, HMC is sort of similar, right? Nuts, it's the same family of algorithms. So nuts is only truth if you have infinite amount of samples and you have infinite amount of time. Then it is theoretically true that it gives the theoretically correct result, right? The exact result. But we cannot run infinite amount of samples, and it's actually in the default setting, it's quite low as far as I know. And also you need to stop at some point. So I wouldn't say that HMC is truth. And just from, it also needs to be analyzed. With all HMC methods, you actually need to be quite advanced in the way you confirm the result. You need to analyze the convergence of your chain, which I didn't do for this particular example because it looks okay. But I would say, and maybe I'm biased a bit, but I would say that the result of RxInfer looks actually better because the variance is smaller. Right, so if we check the value of R, for example, here, right? So the real R was set like 0.9 blah blah or something, and the RxInfer on top actually captured it pretty well with small variance. But if you can see for nuts, it actually gave a pretty big variance. So it says basically, okay, the value of R can be somewhere in between 0.6 and 1, essentially, somewhere in this region, while it's actually, it's just 0.9 or something. The same actually for ADVI. It actually assigned a pretty low probability in this region where the real value actually is. But again, as I mentioned in my disclaimer, I'm pretty much sure this can be improved by choosing a better set of hyperparameters. And probably it can be inferred even faster. Yes. Yeah, the chat, the question in the chat is the following. So just to use HMC nuts for 100,000 samples. Yeah, that's true. We can do that. But then it defies the purpose of being like a fast inference, right? RxInfer. So just to reiterate, nuts, HMC, or sampling-based methods, they're really good if you have infinite amount of compute, or if you have an access to a cluster that runs ChatGPT, then I guess all problems are solved. But for regular people that only have access to Raspberry Pi, this is not an option. So, okay. So there is still some questions in the chat that are coming, but I will just continue because we have only 15 minutes left. So we have some future long-term research ideas about what we want to do. So an interesting idea that we have in mind is that we can actually change the structure on the graph in real time. So imagine the drone, actually a very good example with the horizon. Drone just thinks that horizon is just too large, actually. There's no need for this long horizon. So we can actually change the structure of the graph. We can change the horizon, or we can change the state transition function. So all of a sudden we realized that we deployed our drone with a wrong state transition function, but it already flies and delivers someone's package. So we want to change this state transition function to improve our estimates, right? So it's kind of a very cool idea that we are thinking of. We are thinking about like trading off the accuracy and computational complexity also in real time. That refers to power efficiency, power budget. So in the beginning, if some autonomous system has a lot of power available, it can run a very extensive inference procedure. But at some point, we may decide that, okay, we actually don't have enough energy to do that, so we need to scale it down a little bit. But also, actually, we can trade off different parts of the graph with different set of constraints. So, for example, we can say that this part of the graph refers to an environment, let's say, right? An environment doesn't really change that fast. It changes way less frequently than audio data source, for example, right? So for audio, we really need to do a lot of inference and a lot of very accurate, but for environmental parameters, we may decide, okay, we may want to spend less time on that and infer with less precision. So this is the idea that we want to also play around with. We want to do a multi-agent interaction in the changing environment. So this is actually something that we also already started in our lab, and we actually will have a talk about it on JuliaCon, RxInference.jl, where, yeah, Wouter Newton will talk more about that. But essentially, the idea is that we want to have several agents interacting with each other, all of them with maybe their own probabilistic models, but they are living in the same environment, and they need to have some specific goals, and they need to infer their policies in order to fulfill their goals. And of course, many more. Yeah, we work on the universality still. We want to have some sort of dynamic constraints that also maybe change on the time. Documentation still needs to be improved. That's a never-ending story. Usability, exponential free energy, exponential family support. This is actually what we already doing. Non-parametric distribution support, for example, Gaussian processes. We are working on that as well in our lab. Modular PPL, we actually solved it, so I need to change the slide. And of course, robustness and fixing bugs. It's always the same. Thanks, Vilani, for joining. Yeah, she just mentioned in the chat that he needs to go. So there is a question in the chat. How would you guide structure adaptation, for example, sample actions, which change the model? This is a very good question, and I don't really know the answer for. So this is a research project, essentially. It's not only there are many things to think about. How do we change the model? Do we just change the node, or do we add the node? Or how do we even like debug it? Or what's kind of API in terms of a programming is that? It's a very difficult process. This is why I labeled this as like long-term research idea, is that there is no definite solution for that. But yeah, we are always thinking about it, and maybe at some point we have some sort of revelation, and it's like, okay, this is how we need to do it. Or if you want to collaborate with us, just go to the GitHub discussions, and we can initiate this discussion.
Last time we had actually a talk from gen.jl, and they actually do this, that they can adapt structure. I'm not sure about the details, but this could be a fruitful cooperation to
Yeah.
take a look. And so they had an example, which that's also recorded, that they really create model code. So they have a meta model which creates model code
Oh,
somehow in a way that they can inference about it.
Okay, that's very cool. I will definitely check it out. So that's really nice to know. I actually didn't know about that. I needed to join the Gen.jl.
For me, it was also completely new that this is possible. Yeah.
This is cool. But for us, it's more like an idea of changing the graph structure. But how to actually change it is a research project. And one more thing. So my presentation is almost over. I'm really glad I'm kind of on time. But it has been already mentioned, but we organized JuliaCon in Eindhoven, in the city where I live in. And the cool thing about is that it's going to be in the PC Stadium, right? So have you ever been in a technical conference on a PC Stadium? So this is a very good opportunity for you to join the largest Julia conference in the year, this year. And it's going to happen in July, very soon, and actually in less than 2 weeks. But you, of course, you can still buy tickets and enjoy the conference. And I'm going to be there as well, personally volunteering. And you can always catch me out there so we can have a talk. That was my presentation about RxInfer, path to fast scalable Bayesian inference. So if someone has more questions, this is a very good time. Yeah.
There was a hands up from Albert, I think. Or it was maybe just congratulating you.
Maybe he misclicked React.
Yes,
Albert,
yes.
do you have
I don't have a question. It was a great presentation, Dmitry. So yeah, just misclicked it.
Okay, but what is your reaction?
Reaction is this is the right reaction. Yes.
Okay, good.
Yeah, thank you very much, Dmitry, for giving the presentation today and giving us an introduction to this real industry applications with robots. Awesome stuff. And
Yes.
the drone example from the very beginning really captured it nicely. Yeah, imagining this flying object which needs to adapt to all this uncertainty in the air.
Yeah, it actually, this example has an interesting story. Actually, I've been to Albert's place, and it was like 2 weeks before my PhD presentation, and we were like just brainstorming, okay, how can I present in an interesting way? And then I was like, okay, why not just build a drone? Like, why are not we building a drone? And so we just started to brainstorming and we built a drone. Yeah, this demo was born from a brainstorming session before my PhD defense.
Awesome. Actually, you also use this noise or music and sound processing as an application. Is it actually working? Is it fast enough for such applications?
So we have a paper that is called AIDA, AIDA. So you can, for example, check for details there. I personally never worked with audio processing. I know that some people in our lab, they do work and they do have some result, with audio processing. So
awesome.
Yeah, just to add to that, like actually Ada might not be the good reference for real-time sound processing because it does show that RxInfer essentially can process the sound pretty fast, but that's not real-time. However, there is a paper from Bart van Erp who actually used also RxInfer to implement real-time source separation with nonlinear autoregressive models. So there actually he achieved the real time. So I'd rather suggest this one for reference.
Yes, that's true. It's a good note.
And it was also implemented on Raspberry Pi, by the way. So that's
yeah, awesome. Yeah, I'm glad I asked.
But also I would like to just note again, RxInfer is not really fitted to a particular application, right? In the same way as Turing. So it's more about the way you use it. For example, it can be misused for sure. But we try to just stick to this unique set of requirements that we have, like the efficiency, power budget, memory budget. So I want to create a Bayesian inference toolbox that scales, and then we can use it for different purposes, for audio, for path planning, for drones, or for just medical analysis as well, right? So we are not constraining ourselves to a specific application.
Dmitry, thank you for being our guest, our speaker. I'm looking forward to see you soon in person on JuliaCon, and maybe a couple of you also who will join. Yeah, looking forward for a great event in person. And yeah, thanks for being here online as well.
Thanks for inviting.
Yeah, then have a good evening, everyone. See you soon.
Bye-bye.